In question 5, we're looking at the weights of a sample of 50 babies born at a hospital. So we've got the weight, the frequency, and we've also been given the weight midpoint. We're told that a histogram has been drawn to represent this data, and that the bar representing the weight between 2 and 3 kilograms has a width of 1 centimetre and a height of 4 centimetres. We're asked to calculate the width and height of the bar representing a weight between 3 and 3.5 kilograms. So there's a couple of ways to do this. The first one is just to remember that when we are drawing a histogram, what we have actually got on the y-axis is the frequency density. So the frequency density is the frequency divided by the class width. So divided by class width. So what we can actually do to start off with then is have a look at the frequency density. So here 1 divided by 2 is going to give us a half. We've then got a frequency of 8 divided by a class width of 1, which is going to give us 8. A frequency of 17 divided by a class width of a half is going to give us 34. Similarly here, 17 divided by 0.5 is going to give us 34. And here 7 divided by 1 is going to give us 7. So this is the frequency density. And in the question here, we're told that the bar representing the weight between 2 and 3 has a width of 1 centimetre and a height of 4 centimetres. So the width corresponds nicely because we know that the width is 1 and it is also 1 centimetre on the actual graph here. But for the y-axis, we're told that the actual height, if we measured it, would be 4 centimetres. But we know that actually it's frequency density that's on the y-axis. So the frequency density here is actually going to be 8. So on the scale on the y-axis, this would actually be 8. So what you can clearly see here is that to measure the height in terms of centimetres, it's just going to be half of whatever the frequency density is. So in the question, we're asked to calculate the width and the height of the bar between representing weights between 3 and 3.5. Well, the width is going to be easy. That's just going to be this distance as it is. So that's going to be half a centimetre. The height, therefore, is just going to be half of the frequency density, which we said was 34. Therefore, the height would be 17 centimetres as well. In part B, we're asked to use linear interpolation to find or to estimate the median weight of these babies. So if we've got 50 babies, we are looking for the 25th result. So there's 1 here, there's 8 here, so that's going to be a cumulative frequency of 9. And if we add 17, that's going to take us to 26. So this is the class interval that we are interested in. We know that it's going to start with 3 and it's going to finish with 3.5. And we know that somewhere probably towards the end, because we're looking for the 25th and the last piece of data in this 26, so somewhere near the end is going to be the median. Now we also know that there are 9 pieces of information less than 3, so that value of 9 is going to go here, and there are 26 pieces of data at the end of the range, so that 26 is going to go here, and we know that the 25th piece is the median. So we can now use these proportions to find the value of m, because we know that the ratio of this distance to this distance is going to be the same in both instances. So 25 minus 9, which is going to be 16, over 26 minus 9, which is going to be 17, will be the same as the median, which we can say is Q2 minus 3 over 3.5 minus 3, which is going to give you 0.5. So if I simplify that, multiply both sides by half, and I'm going to get 8 over 17 plus 3 is equal to Q2, and that is going to give me a value of 3.47. Part C is actually fairly straightforward. We're just asked to show that an estimate of the mean weight of the babies is 3.43 kgs, and then use that to find an estimate for the standard deviation. So we've got continuous data. We would normally have to find the midpoint, but it's been provided for us. And essentially what we need to do here then is to find fx. So we just multiply through each of these and complete the table. Now what we need to do then is just to divide sigma fx, which is the sum of this column here, which is going to give us 171.5, and divide that by sigma f, which is this column here, but we're also told that there are 50 babies in total. So 171.5 over 50 is going to give us an answer for the mean of 3.43. So we can now go on to use this answer to find an estimate of the standard deviation in part 2. So because we're using grouped data here, if we look at the variance to start off with, the variance would be the mean of the squares, but here because it's grouped data we're using EFX squared over n minus the square of the means, and again here to find the mean we used sigma fx over sigma f, or n, the same value essentially. That's going to give us the variance. So to work out the standard deviation, all we would need to do is take the square root of that. Sigma fx squared has been provided for us up here, so it's going to be 611.375 over 50 minus, that should be squared, sorry, minus the mean squared, which is just going to be 3.43 squared. And if we do that, we should get an answer of approximately 0.680. Part D is a question which involves the normal distribution. We are asked to find the probability that a newly born baby weighs less than 3 kilograms. Now, in the previous question, we've worked out the mean x bar, which is also the same as mu, and we've also worked out the standard deviation. So we can say that W is normally distributed with a mean of 3.47 and a standard deviation of 0.680. So if we do a quick sketch, here 3.47 is the mean, and we've got something like this. To solve this then, if we're trying to find a probability, this is just going to be the normal CDF on your calculator under the stats option, and in essence what we want to do is find this probability that it's less than 3. So this value here is 3. We want to find this probability. So our lower boundary, remember this is an asymptote and it goes to negative infinity, so our proxy for negative infinity is just going to be e to the negative e to the 99, something like that. The upper bound is going to be 3, and then the mean is 3.47. The standard deviation is 0.680, and you should find that that is going to give you an answer of 0.2546, or approximately 25%. In part E, we're asked to comment on Shyam's decision to model this using the normal distribution. So with reference to your answers B, C, 1 and D, comment on this decision. Well, essentially in B you found the median, C we found the mean, and then D he modelled it with the normal distribution, and we were asked to find the probability of getting W was less than 3. Now, using the normal distribution, we had an answer of 0.2546. Now, let's have a look at how that compares with what we actually found. So the probability that W was less than 3 according to the actual data, the cumulative frequency therefore would be these two together, which would be 9. So the probability that W was less than 3 would be 9 out of a total of 50, which is going to give us a value of 18%, which we can see is considerably lower than the value here that we've got from the model using the normal distribution. So essentially 2 ways you can approach this. The first one is you could say that the median and the mean are broadly the same if you compare the two values of 3.47 for the median and 3.43 for the mean. So you could say that they're approximately equal, therefore there's no skew, so you're fully justified to use the normal distribution to model it. Or the other way you could say is that they are not the same, therefore there is an element of skew, which explains why it's not appropriate to model this data using the normal distribution. So you can argue it both ways here, as long as you've got the reason to justify whether or not he should have used the normal distribution to model this. In the final part of the question, we are told that a newborn baby weighing 3.43 kg is born at the hospital. Now, we should remember that this was the mean weight of the babies born at the hospital. So it says, without any further calculations, state with a reason what effect the addition of this newborn baby will have on the estimate of the mean. Well, since this baby is the same as the mean, it won't have any effect on the overall mean for the sample. But as far as the standard deviation is concerned, because this is another variable at the centre or the mean, it will actually very slightly decrease the standard deviation.